on just around the mountain around here. But I left at a young age, grew up in Singapore. Now I'm working for Mozilla in Mountain View. That's in California in United States. And before I carry on a little bit more, I'd just like to say a few words in Cantonese, if you don't mind. 大家好，我其實係香港人，咁咧就我係講廣東話嘅。不過我都知道，因為我哋呢度有啲外國朋友咧，咁就唔係好方便。咁我亦都知道咧，因為大家身為亞洲人咧，咁啊問有冇問題咧，實係冇問題㗎，係嘛？不過之後咧出邊咧排長龍啊嘛。咁啊，希望大家即係唔好介意啊。即係有啲咩問題啊，即管問。咁咧問問題嗰陣時咧，我就聽得到廣東話、英文都得，普通話你想講普通話都得㗎 ，OK 嘅 ，OK。So yeah, I was just saying that I am basically essentially trilingual. I speak English, Mandarin, and Cantonese. I have spoken about this topic here last year as well. And I also speak about this topic at HKOSCON in Taiwan, but they require me to speak in Mandarin. So that's kind of how I refine my presentation over the next few years. So yeah, back to the topic. Basically, if you see the topic, it says, "Oh, JavaScript fuzzy in Mozilla." So what is it, right? Fuzzing basically it's taking random input and throwing it at a particular program, binary, and see how it reacts. And basically, if there's a program taking any sort of input, it should process it correctly, right? If it's valid input, it should be. Oh, there's more people.
Hi, I'm come to sit to here.
And
First class level.
so wait, where was I? Oh yes, talking about fuzzing, right? Basically, if your program takes any sort of input, it shouldn't crash, it shouldn't run out of memory, it should just keep processing normally, right? It should be processing valid input correctly, the way it should be. It should be processing invalid input correctly as well, because it should tell you that, hey, this is not correct. But sometimes things don't turn out the way we expect, right? If you think about it, humans make mistakes all the time, and humans write software. So in software, there should be mistakes. Oh, right, yeah, we have something now. No, wait, he's using a tablet. Okay, so essentially that's fuzzing in a nutshell. And this topic in computer science has been increasingly more and more popular over the past, say, 5-10 years. In fact, if you look at advisories, security advisories issued by browser vendors throughout, you'll see that, oh, these people from so-and-so, or this particular person from so-and-so, or this particular person with a code name called, say, I don't know, Pinkie Pie or something, has broken a particular browser. And very often, these people use fuzzers, which means that you generate lots and lots of code, thousands and thousands of lines of code. And if it fails, try and find the smallest possible test case and then build towards an exploitation beyond that and after that. But a lot of that is quite heavily technical that I won't go into detail. So here I'll just briefly describe how we leverage fuzzing in our development workflow to help us to find problems. And basically, the more we find, the less outside people find. All right. So let's see. Are you ready? I guess they need a few more seconds. Well, not literally. So yeah, let's see. Let me think. What should I talk about a slide? Oh yeah, I can talk about how I first started in fuzzing. Right. Yeah. All right. I'll talk about my history first. Thank you, everybody. So yeah, at first I was an intern in Mozilla doing Thunderbird QA, and I was finding bugs by hand, and then I would do it in a day. And back then I had a colleague who would come in at night, and I'll chat him up and say, hey, I'm Gary. What's your name? Oh, he says, oh, I'm so and so. Oh, what do you do? Oh, I'm looking at bugs that my computer found yesterday. And I go, wait, I find what? You say your computer found bugs for you, so I don't have to sit in front of the computer and find one. Right? So after that, it became like in a day, I'll do my own stuff, my job, my internship. And at night, I'll learn about what it takes to get a computer to find problems for us. And essentially, ultimately, it's about writing A harness is about writing a harness for the computer where you run your fuzzer 24 hours a day, 7 days a week, and letting it know where it fails. Right? If it fails at a crash, you have to watch the exit code and be able to save it somewhere for you to look at the history and say, oh, it failed with exit code so and so. At this particular moment, it has this particular stack, it has this particular test case, it got reduced to this particular few lines, and then you could even bisect it to say, oh, it was introduced 3 months ago by this particular person. So that's sort of the fuzzing workflow. And initially, we started off with a few machines on a desk, and it became more machines on more desks, and it became machines in the data center. And with the advent of cloud providers, we now use EC2, right? So I think my slides are ready. But unfortunately, I can only show the slides because they're on the internet. They're on GitHub, in fact. But my demonstration is actually in my laptop. So if you want to see the demo, unfortunately, you have to come up to me later. So all right. So that's sort of fuzzing in a nutshell. I have given this presentation in several cities around this past few years in various languages in Japan, Taiwan, Hong Kong. So let's see. Oh, this works. Okay. Yeah. So basically, I've spoken a little bit about what is fuzzing, and I'll also talk about why and what makes it successful, as well as some tips that will make this effective for your own workflow. Right. So this is a XKCD comic, and generally describes that why aren't people working? My code's compiling. And I like to think about it this way, right? Why am I not working? Why am I standing here talking to you? Oh, actually, you know, my code's fuzzing. It's still finding problems for me. Yeah, so basically carry on, right? But yeah, computers, they are great because they just eat electricity, right? They're not human. You don't have to, give them meal breaks. They don't need to sleep. But it also means that they're pretty dumb in a certain way, right? You have to tell them exactly what to look out for. You have to tell them exactly what to find, and things will go wrong, right? For example, when you're testing for bugs, your binary eats a 3,000 line test case. It starts to eat lots and lots of memory, and then your operating system crashes. So your OS crashes. So your OS reboots automatically. Your harness has to be clever enough to pick up from where it left. It has to be clever enough to know that, oh, at this point in time, your binary failed, your OS ran out, and I have to spawn a new directory and try again. But also, it has to keep a record that it failed, right? It has to keep a record that it failed, and such that when you go back in history, you have to know that, oh, at this point in time, it failed. So this was where it failed at. This was what it was trying to reduce, but it caused the whole system to go haywire. So these are basically some of the things you have to deal with, right? So Nicholas Nevercore is one of the low-level tools manager at Mozilla. And something he said is basically the people writing and running fuzzers are by far the most effective QA people. And I would say I agree with that, right? Because instead of me being in front of the computer or anybody being in front of the computer finding problems, you have computers doing it for you. So when you do that at scale, right, the keyword is at scale. If you have cost, I mean, if money is not a problem, you can just basically spin up lots and lots and lots of instances of EC2, of the cloud providers, for example. But of course, realistically, cost is an issue. So whatever it is, it's still more bang for the buck than hiring the equivalent number or resource of humans to find the same thing. Right, so I spoke a little bit of this, basically giving random input to software. We're talking about random valid input, random invalid input, right? It's pretty easy to generate random valid input. You're just throwing in, say it accepts from 0 to 8. You just throw in 0 to 8. That's valid. You could throw in invalid input. If it accepts a function accepts 0 to 8, just throw in 10, 180, minus 1, infinity. In JavaScript, infinity is actually something valid. NaN, which is not a number, stuff like that. But the more interesting bits are when we throw in things on a boundary. So for example, if your functions take 0 to 8, you throw in 8.1, or you throw in minus 0.02, something like that. But this is just an arbitrary example. The well-known examples would be I have a 32-bit binary. What if I throw in a 32-bit number plus 1? It's pretty often that developers don't check for boundary conditions. And it's not their fault. In fact, it's our job to make sure that we find all this before it goes out. So very often when I find problems, I have to make sure that I'm dealing with human relations, and I see, say, I meet people from all over the world, and I will meet them and say, hi, I'm Gary, I'm so-and-so. I will talk about everything under the sun except the problem, and then I'll go, oh, by the way, that's these 3 things that, I need your help. It is much easier than going up to a person whom I don't really know, say, Hayden here. Hi, Hayden, I'm Gary. Yeah, I work on this. We're colleagues. Yeah, work and so. Can you fix this for me? It doesn't feel as nice, right? It's better to go, hey, Hayden, oh, you're from Hong Kong too? Oh, yeah, I'm from Hong Kong too. I love it here. The food's great and all that. And everybody feels happy with you, and then you drop the bombshell. Which is essentially the same thing, except that, it just sounds a little nicer. So yeah, basically, that's fuzzing. It may find easy to detect problems like crashes, assertion failures. These are pretty standard problems to find. Crashes, you have null derefs, you have crashing a particular memory address. You could modify your test case such that it crashes at a particular arbitrary address. So you change your test case to +3+1, for example, and then your memory address moves by 1 byte, for example. That could happen. And then things like these could also manifest in the real world, because when we find it at scale, and very often the real world could have test cases or web pages that basically have the same type of code, except that you're wrapped in all sorts of images and extra JavaScripty stuff. And let me see. Ooh, let me see if I can actually open a link. No, I can't. This is a tablet. All right. So yeah, if you go to Bugzilla and go to 1194022, you actually see a sample test case with information, debug information like a stack trace and what operating system it failed on, what was the version of on the repository that it failed at, and when it happened. Also, we try to run fuzzing using dynamic analysis tools, all right, to find memory safety issues. ASAN and Valgrind, I'd say when ASAN came out, Valgrind didn't become popular anymore. So these are some examples of dynamic analysis tools, and ASAN is really good at finding memory safety errors. I think Kostya from Google works on it, along with a bunch of other people. And its equivalent sanitizers, TSAN, LSAN, find the corresponding problems, threading issues for TSAN and leaks for LSAN. For Valgrind, it was what we had before ASAN came out. But the problem with Valgrind is that it's slow and the overhead is pretty high. Whereas for ASAN, your code is instrumented before compile, around the time of compilation. So your overhead when you're actually running it is, I'd say, a lot lower than Valgrind. So I think people have done some measurements, and the slowdown for Valgrind can probably be 10 times, 20 times slower. Whereas for ASAN, it's probably just 40%, or maybe just a double speed slowdown or something. But yeah, these dynamic analysis tools help us find more memory issues earlier on in a way that we can understand easily. It gives a stack trace and line numbers and stuff like that. Whereas the same problems might not even manifest outside of these tools. Say you run the same test case without these tools, you might not even see anything. You might see an occasional random intermittent crash somewhere, or you might not. Sometimes we have issues with ASLR. So ASLR supposedly protects us, and that's extremely true. But sometimes during fuzzing, it causes the test case to become intermittent. So sometimes we have to disable ASLR on the machine, and then when the test case becomes reproducible, we turn it back on our machines again. So our team now consists of even more people across different parts of the world. We have colleagues from places like Germany, Canada, different parts of the United States, and I'm the sole representative in Asia. So there are some fuzzing tools that are pretty well known out there, some of which we create, and most companies that write fuzzers tend to keep it close to themselves, although there are some open source things out there. The first well-known fuzzing tool was actually MangoMe, created by Michael Zalewski. And in the next slide, you'll see another thing that he wrote, which is AFL, and that is pretty popular with people in the fuzzing area around the world. So Jesse Ruderman was the one who wrote JS Fun Fuzz, and is the one that finds lots of JavaScript issues, things like type issues, threading issues, but generally only with JavaScript. We also do have fuzzers in DOM. In fact, that DOM Fuzz right now, I'd say, is close to being deprecated. We have a new replacement coming up, DOM Fuzz 2. But if you follow the links, you can see the source code for both of them. Right, and that's Langfuzz being worked on by Christian Holler, also one of my colleagues, and there's Peach, famous fuzzing framework by the Peach folks. There's AFL, and there's Dharma, also by one of my colleagues, Christoph. Right, again, this is a change from the last few years. It used to be that we are one of only two companies, along with Google, to offer a bug bounty program. But as you can see right now, most, if not all, of the major browsers have bug bounty programs, which may or may not pay out for your particular bug in browser. So it's at their discretion. It's at their discretion as to whether they pay out for your problem or not. But basically, the point I'm trying to make is the browser vendors are paying for bugs out there right now. Why? It's because there are actually more entities paying out in similar areas, just that they're not part of these organizations. For example, like ZDI, and if you watch the news, sometimes there's the Pawn2Own browser competition that happens in, I'd say, Canada in March every year, perhaps. And there's always news where they go, oh, this particular browser is exploited. And the people probably pay out tens of thousands of US dollars, hundreds of thousands of US dollars. So if you convert that to Hong Kong dollars, it may be up to $1 million Hong Kong dollars per bug. I mean, per exploit, which probably sometimes doesn't only consist of one bug. But if you can prove the exploitation, you get a certain sum of money. And all this is actually even excluding some of the darker areas of the industry out there, where you have brokers buying and selling such bugs. And if they don't go through the official programs, if they don't go through Pawn2Own, the money that they receive may even be higher in those areas. In fact, I think some time ago, was it the FBI or something, the CIA and the FBI wanted to access the data of a particular phone of a particular person of interest, and it was reported that the FBI, CIA paid a 6-figure US dollar sum to get that data. All right. So we are seeing this part of the industry grow, which means if you think about it from the point of your company, right, you have to find more of this yourself, so you don't get, the bad end of the stick out there. Right? Use after free in Mozilla's bug bounty program can possibly be worth 3 to 5K US dollars, and bug counts for just the two fuzzers that I have been looking at the past few years is easily 7,000. More than 10% of them are critical security bugs. There's been lots of talks at various security conferences worldwide. Black Hat and DEF CON are well-known examples, and there have been articles in industry on Pwn2Own, which is a little bit of what I spoke about just now. So what do you look for in your tests? Basically, you have to consider, is your program written in an unsafe language? Is it in a sandbox? Is it parsing input that can be controlled? Right? By unsafe language, I mean generally C++. But say if you wrote it in Rust, it doesn't mean that you're free of issues. It's just that the issue is being exposed in a different way, or it's being controlled in a certain way. Or in the case of null-derived, it might just not exist. Are you considering your boundaries, security boundaries correctly? And basically, what if at a particular point in time, there are other security researchers reporting bugs in a particular area that you're not looking at? One excellent example is in, I think, Pwn2Own last year or something. There were several teams of security researchers that hit Firefox using typed arrays. So apparently our typed array implementation wasn't up to speed. And I think it took us a few months of solid work by one engineer to fix that whole typed array issue. So yeah, some good starting points would be, if your program is pretty big, then you have to think about how to isolate them into different components, different modules. For the case of the Firefox browser, we're looking at the media shell, the JavaScript shell, because their startup and shutdown times are quite fast, like really, really fast, 0.0 something seconds. Whereas if you turn on a browser, maybe it takes a second or two. And in the long run of, in the grand scheme of things, when you're doing things at scale over like 3,000 runs, then your overhead is 1 to 2 seconds times, say, 3,000, and it's pretty high. So isolated modules, having them smaller is actually a good thing. But of course, it doesn't mean that you don't test with your larger product, because there are some problems that can occur with the interaction of the different pieces in the program. So basically, if your project is large, if your project is large and you have to prioritize, right? You're looking at many bugs, you're looking at lack of tests in general, because you don't have time to write your tests, you don't have enough manpower to write the code and fix the bugs, and there's resistance because people who don't believe that that's actually a bug, or they don't believe that a bug is actually important. So sometimes we have things like fuzz blockers, where we have a bug that is actually just a print statement, but it dumps so much information that our logs are gigabytes. So it's actually preventing us from finding the more serious issues out there. So those kind of things we have to get developers to fix for us, but they may resist because they may think it's not important. So that's why a good relationship with good working relationship with the developers is really important, right? And basically, it can be hard to find serious bugs, but it can be mitigated by using dynamic analysis tools, right? So basically, JS team in Mozilla didn't start off being such good friends initially, but over 2-3 years, they realized the value of it, because we would come by with nice test cases, with nice stack traces, and it was always better to look at a fuzz bug than a real-world website which had 3 megabytes of code, which could change anytime. And after a while, we started working well together, and we have been working well together easily for, I'd say, the better half of a decade now. So, but it wasn't that easy, and it still is not that easy with teams who are not used to fuzzing initially, right? And it's interesting. Sometimes developers will say, "Oh, I'm going to wait a day and see if the fuzzers show anything up before I try to reduce this mega website." Right. So here's another quote, this time from a community member. Arai-san is someone from Japan, and it's mentioned that fuzzing is an effective way to find corner cases, and that a comprehensive report can actually provide more information, so you don't have to keep asking for more information. And usually, very often, when I sit down with a developer and I show him or her a particular bug, it's usually magic to me because he or she looks at it for 3 seconds and go, "Oh, I know what's going on," and I go, "What?" But yeah, that's because we found the right person, right? Because the code is fresh in his or her mind, and him or her worked on the code maybe 2 weeks ago. It's always easier to get something from someone when they've freshly worked on it than say 3 years ago, right? Right. So generally, we work as a team, right? They fix bugs for us. We have to ensure that tests land on the trunk such that we use these tests to create more test cases, right? Our fuzzers use generational fuzzing, use mutational fuzzing. Generational fuzzing means it generates based on the grammar of your language, generates random stuff. Mutational means it takes a starting point instead of starting point of nothing. It uses the starting point of an existing test that was known to break. For example, you could have a test case that failed at 0.5 and the developer fixed it for 0.5 but failed to fix for 0.4 and 0.6, something plus minus. That's why mutational fuzzing works well, because probably a developer never did not do a good job of predicting what inputs could go in that area, right? So when developers add more assertions and we test them in isolation, we've touched a little bit about this. Using dynamic analysis tools, we can help to find more bugs together. The more bugs we find, the less bugs people outside find. Right, I've touched on this a little already. So what are some of the pitfalls, right? If we use automation frameworks for fuzzing, when the frameworks go, say when they're deprecated, you have to write something from scratch again. Or devices may not be powerful enough. When you fuzz on, say, phones or something, on ARM, these ARM devices may not be powerful enough to be run 24/7 over an extended period of time. So probably you have to write a simulator for that particular architecture to be run on the cloud instead. Right, so some of the factors of success is patches must land on the trunk. When regressions occur, you have to back out. You have to be really strict. And then, of course, ensure that the bugs are fixed and the tests are not disabled often. Okay. The workflow should involve the fuzzer, the instrumentation, where you're instrumenting the code for the dynamic analysis tools. You monitor such that it's running 24/7 properly. You bucket the issues. Say you have different stack traces that differ from each other just by one line. They're actually essentially the same thing. And then you will reduce the test case and bisect them automatically, all done automatically. So we have some projects that will help with all these, and all these are open source. Basically, all of our code reports to a local instance of Fuzz Manager. That's the reporting tool. And we have the harness for JFunFuzz. In fact, JFunFuzz is present in FunFuzz repo as well as a tool to manage EC2 instances called IKEA. It's all via the command line. Oh, swipe the wrong way. And we have test case reducers. And in fact, right now we're working on splitting up the automatic bisection into a separate repository. So all those are in the works, and you might want to follow Mozilla Security at GitHub, right? And we also have a fuzzing framework in JavaScript. Right, we don't have time for Q&A. We can line up outside for Q&A, apparently. But yeah, basically we are on channel #fuzzing on IRC, and basically, feel free to ask questions, feel free to ask, and I hope to talk more in depth when, in the future. Is there any questions? Do I see a hand? No. Okay. All right. With that, thank you, and yep, thank you. I hope to have some conversations with you. Thanks.